Hello, everybody. Welcome to today's seminar. So we have the second. We have the pleasure of having John Harnad, with the president of this Matrices group at there. He will tell us about the Hamiltonian structure of rational isomonodromic deformations.
Okay, so it's a pleasure to talk to you again. It's been a while. So this is a very historical topic. As a mathematical topic, it goes back at least until the end of the 19th century. And the amazing thing is that even now, 2023, there are fundamental results which are still being developed. One would have thought that it's already shot its wad, but it hasn't. There's still plenty of new things to find. So what I'll report today is recent joint work with Marco Bertola and Jack Lipkowitz, but in my own interest in subject that goes back some 30 years. So in fact, I'll be referring to some history, but I'm going to refer to much earlier history first. So here's the introduction. There's no pointer, so I'll first just describe a historical introduction and some applications and for example before getting into the material. The main thing is there's these equations. They're equations, nonlinear equations, but of a very special kind, which many of the people here have studied things like Painlevé equations and so on. And they have plenty of applications in a whole variety of physics topics. And but the new thing is nothing really new. They've been developing, like isomonodromic deformations has been developing part and parcel of the theory of integrable systems. It's really a sort of a shoot-off of the theory of integrable systems. You'll see in what way in the talk, but it's basically the renewed interest in it is as an outgrowth of the modern developments in integrable systems theory and inverse spectral theory, Riemann and so on. Anyway, so the key tool, which I'll be talking about, I'm not going to be talking about solutions to these equations. I'm going to only talk about the structure. The structure is rather important. And the fact that all these equations, it's really a rather vast family of equations, can be viewed as Hamiltonian systems. But the key singularity in the thing is that they are non-autonomous. So everything, most of what is done with integrable systems refers to autonomous systems, which means they're systems of differential equations in which the independent variables do not appear as explicitly as part of the equations. They're just there as independent variables. So let's say in the simplest case, non-autonomous would be a vector field which is time dependent, so it's changing with the same time parameter that's causing the system to evolve, and that would be non-autonomous. So isomonodromic deformations generally are non-autonomous systems. They're sort of the non-autonomous cousins of autonomous systems, which also have the same Hamiltonian structure, but they're a good deal easier to deal with. And that is the main substance of the theory of integrable systems. The key Hamiltonian structure is the same as for the standard integrable systems theory, which is based, you've probably heard of the notion R matrix and Yang-Baxter equations. So, oh, by the way, there's also classical and quantum manifestations of this. I will be mainly today talking about classical, but there are certainly many, many applications, even of the classical isomonodromic equations. There are many applications to quantum problems where you're computing things like correlation functions in either a statistical mechanical or a quantum many-body system or a quantum field theory. And the equations that determine these correlation functions themselves are isomonodromic deformation equations. So there's a very, very close interplay between classical and quantum. So I'll talk about this general R matrix theory, just a special case of it, the so-called rational split R matrix structure, which is plenty for covering today. It's a more general theory. And I'll talk about the Hamiltonian structure. I have to give some review of stuff that maybe not everyone is familiar with, but it's basically very part of the very core of the theory of linear differential equations and with singularities. And the isomonodromic deformations have to do with how solutions to these linear equations transform as you move around the singularities. You analytically continue, you don't necessarily get back to where you started. And that's what's called monodromy. But we're not just looking at the linear equations. The linear equations are there, as always in spectral theory. But the equations we're looking at are things like Painlevé and so on. Those are nonlinear equations. What their role is to describe deformation classes of the linear systems, depending on parameters, which have the property of preserving the monodromy of the linear system. In the usual integral systems theory, what is preserved is the spectrum of the linear operator, isospectral deformations. That's the typical way to formulate the modern theory of integral systems. In this case, I'll explain what it is. It's not isospectral, it's isomonodromic. So it's a different thing, and yet the same tools, the same phase space, etc. enter. So I have to recall sort of some textbook material because I can't presume that I'm familiar with that, but it's a very standard thing that goes back about 100 years. And then I will define what the Hamiltonian, well, first of all, what the Hamiltonian structure is, and then what the Hamiltonians are that drive these isomonodromic deformations. And then that's very closely related to my favorite topic, the theory of tau functions. Tau functions for isomonodromic deformations are practically the same thing as looking at the Hamiltonians that drive the system. Basically, the logarithmic differential of the tau function has as its coefficients all of the mutually commuting Hamiltonians that drive the system. And okay, the rest will be technical, so I'm not going to do that. So here's a brief history. It might precede this, but at least it goes back to 1889. Classical works of people like Picard, Painlevé, Fuchs, and Schlesinger. Big work by Schlesinger, 1912, which was sort of the pinnacle of where things had reached until then. In which what they were doing, I mean, Painlevé started this business of, or he did others, did similar things at the end of the 19th century, studying nonlinear differential equations of a very special kind. The main thing is that they have this Painlevé property, which means that when singularities develop in the solutions, these singularities either do not depend on the initial conditions, so it's sort of universal, or they are just poles. So the only movable singularities that exist are the pole singularities. That's the Painlevé property. That's very closely related to this isomonodromic property. Okay, so in 1913, Birkhoff extended the class of equations that these, well, actually already Painlevé did do some other examples, but the typical system was the Schlesinger system. The Schlesinger system, as you will be seeing it as a second example, is a linear system. You can always write it as a first order system just by making more dependent variables. So you can just take the, if it's a scalar system, you take a higher degree, you just put in the derivatives in the dependent variables. So you can always reduce it to an equivalent first order system. And the Schlesinger, and that's the only kind of system I look at, the Schlesinger equation, is the special case of all possible isomonodromic deformations of first order systems in which the singularities are so-called regular singularities. That just means for first order systems, the coefficients in the system have first order poles, nothing but first order poles. That's called a Fuchsian system. If they're only only first order poles, then really the monodromy data is the full set of data describing it, and there's a sort of inverse problem, just like the inverse spectral problem. Birkhoff, I think, was the first to really systematically look at more general monodromy data when you don't have Fuchsian systems, and you don't have first order. And so that involves irregular. I'm only talking about isolated singularities and a finite number of them. So that really means a first order linear system in which the coefficients are rational functions, but possibly with higher order poles. Think of it in a Riemann sphere, all you can do is for isolated finite number of poles, it can only be a rational function. So he introduced this notion of generalized monodromy data, which in addition to the monodromy, which is very simple, includes something much more subtle, which maybe not everyone has encountered, but is really very fundamental in physics applications, and that's Stokes phenomena. We know that in optics and other applications, we need to use the notion of Stokes parameters and Stokes measures to describe the asymptotic behavior near to a singular point that is not a regular singular point. So he introduced that as part of the generalized monodromy data. And also you have to have a sort of reference point. You take some reference point which you connect up by paths and then with continuation to all of the other singular points. And that introduces a little bit more data that's called connection matrices. And we'll see that that gives you the general stock of what is called generalized monodromy data. And the equations we'll be studying will involve deformations that preserve that data. Monodromy matrices, Stokes matrices, connection matrices. Now that's all very old stuff, but the renewal of interest started with the rebirth of integral systems. I won't describe the history of that, but there was a very important contribution from the Japanese school of Sato and his students, and they completely brought out of the doldrums the theory of isomonodromy and generalized it, the theory. So they took the most general systems that Murkoff had studied. He didn't study the deformations, he just studied systems with irregular singularities of finite number of them, and gave the correct parameterizations and so on, but he didn't study the problem, the analogous problem to what Schlesinger had studied for Fuchsian systems, namely, what is the most general way you can deform these systems while preserving the generalized monodromy? So, especially Jimbo, Newell, and Leno, who were students of Sato, took this up and plunged it into the general theory of soliton theory, inverse spectral theory, but this really was not inverse spectral theory. And the subtle relationship between the two was at that time not very clear. Okay, then I'll just say there has been a history, but not such a rich history, of studying these things from the viewpoint of Hamiltonian equations. Everyone knows what Hamiltonian dynamics is about, but I warn you that these will be non-autonomous Hamiltonian systems, and that's a key ingredient. So that was also touched upon an example historically. The most recent contribution within our present epoch, or at least my generation, was Okamoto in 1980. Many of you were not yet alive at the time, but it's still the last 50 years or so. And they introduced, Jimbo and company, the notion of isomonodromic tau functions, which is for a class of subcases was intimately related to the Hamiltonian structure. They did not succeed in giving a Hamiltonian structure the general case, and that's what we finally succeeded in doing with Marco and Jack last year. So I'd say there's still fundamentals that remain to be explored. Okay. I think I'm taking too long in my introduction. I better speed up. Here's a list of some physics applications. This is the positive mathematical physics talk. I'm mainly going to be talking about equations, mathematical methods, but I want you to know that there's a huge range of physical problems in which such equations arise, and the theory of such equations is just as important as the theory of various other special functions like trigonometric and elliptic and so on. Well, the Painlevé functions also play an important role in physical problems, and here are some of them. First of all, in the 2D Ising model, as I said, it's a quantum problem. Spin-spin correlators satisfy, when properly parameterized, satisfy the second Painlevé equation. That's an isomonodromic deformation equation, and there's a special solution which describes it. And that was studied way back in the 1970s by Wu and Tracy. Already in quantum mechanics and statistical theory, there are applications. Integrals quantum spin chains and also quantum gravity, which seems like a totally unrelated subject, but both of those lead to Painlevé type equations and isomonodromic information. Already in the work of Jimbo and company, they studied field correlators for Bose gases, so repulsive Bose gases, and there also the Painlevé fifth equation came up, and that turned out to be a key ingredient in the characterization of the correlation functions. Then there was a huge development, which is still resonating till today, in the spectral theory of random matrices. So random matrices were brought into physics by Wigner. I won't go through the history, but they have much more modern applications. When studying the statistical properties of the spectra of large nuclei, which were developed already by Wigner and Dyson and others, but some very important properties, namely the correlations of the eigenvalues, both in the bulk part, because there are certain regions where the spectrum is continuous, both in the bulk part, which actually is governed by Painlevé 5, that was shown by Jimbo, and at the edge of the spectrum, which is governed by Painlevé 2, and that was shown by Tracy Whitman. Lo and behold, three new standardized statistical distribution functions, the Tracy-Whitman distributions of type 1, 2, and 4, came into the literature, and suddenly people found universality. That is, these properties, this behavior, the behavior of the, let's say, the random matrix spectra in the limits of large matrices near the edge, occurred in dozens and dozens of other problems in the quite modern developments so related to that, and that was under the heading of universality. It turned out, well, one thing, there's no number theorists in the audience, but the number theorists are all excited about relations between the zeros of the zeta function and the spectrum of random matrices. There's the same fundamental correlation function that enters, and that was discovered 40 years ago. But that's just the pure mathematical. So they belong to the same universality class. That doesn't mean it's the same equations, but it's the same distributions statistically. Then there were in quantum field theory, the topological field theories, and in particular the theory of Frobenius manifolds, which was developed by Boris Dubrovin. And what he did, if you look at his description, I mean, it's a way to calculate, again, correlators in topological field theory. We see a lecture which involved that WDVV equations. Yes, last week, WDVV equations determine these correlators, and that was made into a whole subject by Boris Dubrovin. And he showed that it was equivalent to a family of isomonodromic deformation equations. So they are back in the same territory when dealing with topological quantum field theory. There are others. There was some remarkable work of Nekrasov and Shekashvili about relating supersymmetric angles theory to isomonodromic systems. And I can't go into that, but it also had to do with certain moduli spaces for the solution of the supersymmetric equation. And finally, quite recently, in ongoing work, there's been a very close connection made between conformal field theory and isomonodromic informations. Basically, the isomonodromic tau function, which we'll be encountering later on, admits a sort of combinatorial expansion. It's an expansion in infinity of different variables, but each of the terms is interpretable a little bit like the speaker last week as expansions of operator product expectation values. And so those involve these conformal blocks that we was talking about. I call them certain else. Okay, so that's just a list of physics applications. From now on, I'm talking math, but I have to do that at least to justify this within this series. Here's an example. There's a friendly, simple example. If you just open Whittaker and Watson, I don't know which chapter, you won't see this, but you will see the Weierstrass equation. which has almost the same form as this. The only difference between this equation and the Weierstrass equation, which describes elliptic functions, basically the equation describing elliptic functions, is t. If t is the independent variable, if that were there, or if t were replaced by a constant, this would be the Weierstrass equation. So what this is a non-autonomous deformation of the Weierstrass equation. That is a key element that we should bear in mind all the time. But it has been studied, well, it's exactly what goes into the Tracy-William distribution. The tau function for this equation, and the solution is exactly what describes the edge behavior of the spectrum of large random matrices, and many other things, quasi-crystals, and a whole bunch of things. Anyway, the idea is, this is the, take that as the paradigm of a relatively simple, nonlinear, non-autonomous equation that satisfies the Painlevé property. We call it the Painlevé property means that you have a solution in time, let the time be complex, and analytically continue it until you hit singularities. The only singularities that you'll meet in solutions to this equation will be pole singularities. You could have some logarithmic ones, but they will not depend on the initial condition. There'll just be some constants. Actually, I think there aren't even any logarithms. So that's the Painlevé property, which was the main motivating theme for all of the work of Painlevé and his successors. But he didn't immediately look at it as an isomonodromic differential, but it is. Jimbo, Miwa, and others put it into this context. And here is the isomonodromic system that it represents. Now, everything in this example is paradigmatic. So if you understand this example, you'll understand all the rest of the talk, at least all of the ingredients. What we have here, this is a 2x2 matrix. This is a fundamental system. So we have a first order linear system for a vector, two-component vector. And the space of solutions is two-dimensional. So we have two linearly independent solutions. And this is a fundamental solution consisting of an invertible matrix whose columns are two linear independent solutions to the same equation. So psi takes values in the general linear group, and z is the well, we sometimes call it the spectral parameter. The differential equation is always in the complex plane, and it's the first order differential equation, rank 2. And that is the equation whose monodromy we want to preserve. I'll make the monodromy clearer later in the talk, but there is the only singularity that is relevant in this system, because L is a very simple 2x2 matrix, which is a second degree polynomial in Z with standardized leading coefficient. It's a quadratic. The only place where this has a singularity is at infinity. It looks like a second order pole. It's really a fourth order pole, because the relevant thing in all of these things for geometrical reasons is not L, which we call the lax matrix, but L dz, a differential form. And the reason is because what we're dealing with is a covariant derivative. Covariant derivative, just in the complex plane, but this is a component of a connection form. Like in gauge theory, it's a connection form, it's one form. So you should take this matrix and multiply it by dz to get the connection form. And that dz, if you change variables at infinity, and look at zeta going to 0, that gives you something like v zeta over zeta squared. Then you get an extra 1 over zeta squared, and that gives you zeta to the fourth. So it's really a fourth order singularity. One less than the degree of the pole is called the Poincaré classical differential equations theory. One less than the degree of the pole is called the Poincaré index. That tells you to what extent that singularity is an irregular singularity. If that were 0, you'd have a first order pole, and you wouldn't have any irregular singularity. So it's the defect which makes it irregular that is contained. But in this case, the Poincaré index is 3. is a whole degree 4.
What are x2 and y1?
Those are just, for the moment, they're coordinates, but they're deliberately written in a way, in a suggested way. They're just ways to parameterize. In addition to t, it's just a way to parameterize. You can standardize such things as the leading term just by changing bases and so on. But for the moment, they're just 4, as it will turn out, canonical variables. It will be canonical coordinates on a 4-dimensional phase space. But I'm not explaining now because it's just an example. But that's just part of the parameterization, which will lead to this. So u will be a function of all of these coordinates. And okay.
So I'm curious, is there any way of constructing a similar fundamental system, different one, with all these properties you are telling?
Yes, it's not. You mean for the same equation?
Yeah.
There are lots of. I'm not going to talk about that because it's taking away from the subject, but there are lots of equivalents, and there are gauge transformations. There are transformations of the independent variable z, a linear fractional transformation. All of these will preserve the structure and will give you the same equation, just parameterized in a different way. So that's the object of interest, which we don't want its monodromy to change. I've said what the monodromy is. Certainly there's the monodromy going around the point of infinity, but when you have just one pole, there's never any monodromy, because going in the Riemann sphere, one point going around it is the same as going around the outside, and there's nothing in the outside. So in fact, there's no monodromy. The monodromy is just trivial. What is not trivial is the Stokes parameters. This is a Stokes system, and that we'll talk about. So there's Stokes parameters that have to be invariant. There's no connection matrices because there's only one pole. So it's really just the Stokes parameters at infinity that are the invariant generalized vertical monodromy data. How do you, so what is the rule? The statement is that its monodromy, whatever that is, those Stokes thing, will be preserved if and only if the same fundamental solution to this system satisfies, with respect to deformations in the t parameter, this system, where u is also very simple. All of these formulae will just be special cases of a general formula that I will announce before the end of the talk. It's just a special case. So this one is parameterized for God knows what reasons exactly in this way. Okay.
But u of z has no t dependence.
U of z has no explicit t. But of course, x1 and y1 are going to depend on t. It's a non-autonomous system. So the compatibility of these are like two components of the covariant derivative, one in the z direction, one in the t direction. So we're looking at the enhanced space, the z space and the parameter space, 2 dimensions. And the fact that they're compatible means you can cross differentiate, which just is geometrically fancy way to say that the curvature of this connection in this 2-dimensional space is 0. That's a 0 curvature condition. This is everything that you see in this example will occur in the general case. And okay, I said it was canonical coordinates, so I want to think of these as canonical coordinates on a 4-dimensional space. The t's, by the way, are not part of that space if you think of it as a symplectic space. But if you think of it as a Poisson space, the t is a transverse parameter which takes you from one symplectic leaf to another. It's what's called the Casimir invariant. Anyway, so this just take the x's and y's to the canonical coordinates. Now change, don't ask me why, but change coordinates in the canonical way to these new coordinates, E, U, A, and W. Where here's the definition. It's a canonical coordinate change, preserves the canonical one form. And the Hamiltonian that drives the system is going to be a spectral invariant, an invariant of we call this the Lax matrix. That has a spectrum, and it's characterized by its characteristic polynomial. You write down the characteristic polynomial of this. It gives you a second-degree equation in the eigenvalue, and that equation is the spectral curve. The coefficients of that curve are the spectral variants. They're invariant, obviously, it's the determinant of L minus Z. It's obviously invariant under conjugation. And that's what we mean by the spectral invariants, or all the conjugation invariant functions of L. And the Hamiltonian and the T parameter, both of them are spectral invariants. So you have it right here. The T is not yet written, but it also can be written in this form. Here, the H is obviously written as a spectral variant. If you trace it out squared, and then you do some residue calculation, but it's obviously conjugation invariant. That will be the Hamiltonian that drives the system. And A is also spectral invariant, but it's a conserved quantity. Poisson convenes with the H, and it is actually autonomous. It doesn't depend on T. So that's also another spectral invariant. This is the residue of the residue of trace it out squared divided by Z, and this is the residue divided by Z squared. So you have these two conserved quantities. A, rather W, A should be thought of as the conserved momentum. W is the conserved position. If you remember your old terminology, this is what's called a completely ignorable system. The Hamiltonian does not depend on it does not depend on W. So we've already gotten rid of two of the variables. One of them is a conserved quantity, and you get the Hamilton equations. And this is Hamilton's equations for the system. U and V. Now U is the thing that satisfies the Hamilton equation. V is its momentum. That's the position. It's the momentum. And so you eliminate the first degree equation, you get the second degree, and you're back in Hamilton. So this, in a nutshell, without explaining how the parameterization became, this in a nutshell is what is going to happen in every example that we do. Now here's another. This I'll do much quickly. This is Schlesingers system. Schlesingers system. The equation involves a lax matrix with any number of first-order poles of any rank. That's the most general so-called Fuchsian system, in which there are only regular singular points. The singular points are where Z equals these parameters. They're all distinct. So that's the most general higher rank Fuchsian system. And in order to preserve its monodromy, we have a first order equation like before, but where the right hand side is replaced by this rational function, rational matrix. We want to preserve the monodromy of this, and now it's really only one. There's no Stokes, because there's nothing irregular. You want to be sure that the monodromy, basically, I'll say in words, it's an easy idea. You take a fundamental solution and you analytically continue as you go around the singular points. So here's, let's say, a Riemann sphere. CQ1. It's the North Pole, that's infinity. And you have these various points, C1, C2, etc. And you have a solution, psi Z. Now you think of the fundamental group, you think of the paths, equivalence classes of paths. In the punctured sphere, you take out these points. And, well, the fundamental group is very simple. It's generated by all of the loops. You have a loop around this, a loop around that, a loop around that. And all products will give you all homotopy classes of closed loops. So what happens is when you go through any path, let's say we take this path, which encircles the first singular point once. When you analytically continue this, let's call that gamma. So you act by gamma on this. It will still be the same equation, still satisfies the same equation. So the solution can only be a linear combination of the two solutions that are formed from the column. So there's a monodromy matrix which relates the two going around once. That's the first monodromy matrix, and that doesn't depend on Z. It's just the homotopy class of the path. And same thing for all the others. And then you just generate using all of the monodromy matrices, you generate the full monodromy representation, which is a representation of the fundamental group of the punctured sphere minus the points C1, etc. That's the monodromy representation. There's some little details about choosing a reference point, but I won't go into that. So this is all the data that you want to preserve. And Schlesinger showed already that in order to the necessary and sufficient condition under deformations, the only parameters that you can play around with are the locations of the poles. So if you fix the poles, you can't do it. You give the monodromy fixed poles, you can't change the coefficients of the lax function. But if you allow the poles to move around, it's all topologically equivalent, ontopically equivalent. Then there's a dependence of the lax matrix, of all the lax matrices, on these deformation parameters. And these are all R by R matrices, and the theorem is that the dependence is such that the monodromy, the monodromy matrices are independent of the deformation. It doesn't matter what the poles are, as long as the second, the deformation equation, is satisfied. That's the necessary and sufficient condition for preserving the monodromy. So once again, we have an overdetermined system. We have a z derivative, and we have partial derivatives in all of the c directions. They all commute. All of the covariant derivatives commute, and that gives you this system, which is called Schlesinger system. Schlesinger didn't point out the Hamiltonian structure of this, but it's known. This is a Hamiltonian system, non-autonomous, and I'll tell you very quickly. Then I think I have to accelerate a little bit. So what you do is again take residues or traces of the square frontal axis. These are the Schlesinger Hamiltonians. And you introduce a very natural Poisson structure, which most of you, I hope most of you have encountered. It's called the Lie-Poisson structure. It's just dual to the Lie bracket structure on the algebra. Does everyone know what the Lie-Poisson structure is? It's the canonical thing. It goes back to Lie. So if you know the algebras, you should know Lie-Poisson structures on their duals. So here it is. Every one of these numerator matrices belongs to GLR, and they don't see each other. They Poisson commute with each other. It's just a direct, just a product space. And they don't. So the Poisson bracket anything from one of these with another one, it's always zero. But within each GLR, this is the standard. You'll recognize it as the Lie bracket of two basis elements in GLR. It's a Poisson bracket. That's the dual. The Poisson bracket. If they're different, then it's zero. If they're the same, then it's given by this formula. This is the standard thing for GLR. So that's the Lie-Poisson bracket. That's what we use. That's the phase space. It's the space of n tuples of R by R matrices. And so the Hamiltonian equation, and now I'd like to draw your attention to this next statement, very important. The Hamilton's equation says the partial derivative, if I look at C mu as the time variable that's evolving, a pure Hamiltonian equation would be this, would be the Poisson bracket with the Hamiltonian. Right? That's one form of Hamilton's equation. But there's an extra term involved because L not only depends on C through the numerator variable, but also there's an explicit dependency here in the denominator. You have to take that into account when you differentiate. It's not part of the Hamilton's equations. So you have to add that. That's an explicit derivative. And that's very important. Now there's something magical that happens. That's this object, which is not sufficient to imply zero curvature, is identically the same. You can look at it directly. It's identically the partial derivative of the lax matrix with respect to the youth pole variable is exactly the same, negative, as the derivative with respect to z of the other matrix appearing in the deformation. So this is the original equation, this is the deformation equation. The partial derivative of this guy with respect to z happens to equal, you can just look at it, they're both equal to L over Z minus C squared. It happens to equal the explicit derivative of the lax matrix with respect to the C variable. Z minus C, so it's a flip of sign with extension. The fact that these are true means I can write this in the zero curvature forms. Now I have the zero, this is the zero curvature equation. Exactly the statement that the covariant derivatives amongst themselves can do. And of course, also the covariant derivative, sorry, this is wrong. This is u. I gave a name to it, u mu and u mu, where u mu is just by definition L mu divided by mu. So this is the zero curvature condition, and then we also have actually these are redundant, but let's write it down. These are the curvature components, they're all zero. It's a zero curvature system. And that's just the Frobenius integrability condition for this linear overdetermined linear system. So that's what that's as far as I'll go now with the Schlesinger system. We'll come back to it at the end of the hour, once we know more. Before I go to the general case, are there any questions? Basically, everything you saw in these two examples will now just be generalized. And everything that we saw will be reproduced in special case. So you've seen the essence of the results, but now what are the results? What replaces the decimal brackets? The matrices. What replaces the Hamiltonians? What replaces the t variable? Which deformation parameters can you have? All of this is part of the theory. Questions? Okay. So now we're going to put ourselves in very general case. So we now have a rational lax matrix with poles of any degree, whether at finite points c mu or at infinity. So again, the d is the Poincaré index, which is one less than the degree of the pole of L dz as a differential form. Okay, so we have these parameters which characterize the lax matrix, the location of the poles, the degrees of the poles, and there is a normalization that we can do, just like in the family 2 case, where we can take the leading term here and just standardize it to be a diagonal matrix with distinct eigenvalues. We'll do that. That's generic condition. The degeneracy is called the resonance. We won't deal with that today. And we look at such linear first order Fuchsian differential. Sorry, not Fuchsian. Not if all of the Poincaré indices were zero, Poincaré indices were zero, this would be Fuchsian. That would be the Schlesinger system. We get back to Schlesinger system. But in general, it's not. But still, we look at the linear differential equation and we ask ourselves now, what are the deformation parameters? For Schlesinger, we only had the location of the poles. For Painlevé 2, we had something else which was not a location of the pole. And I mentioned to you that it actually is sort of a Casimir, and that's what's going to happen. Now let's look at that. What we do is we rely on the old results to find what are the appropriate information parameters. So he not only identified the generalized monodromy data, monodromy Stokes matrices and connection matrices, but he also identified the local asymptotic behavior near to every singularity in terms of certain parameters. And those are the parameters that we will allow to vary. So just for notation, let's put in a local coordinate in the neighborhood of every point. So near to z, we'll call z minus u, z mu. This is just so we can present all the coordinates and do. And at infinity, we'll just call 1 over z the coordinate that is there. Okay, so this is Birkhoff, 1913. For such a linear system with these singularities, there exists a formal series. This is not necessarily convergent. Usually it's not convergent, but there exists a unique formal series solution in the neighborhood of every singular point of this form. So basically, you have a factorization into two parts. If it weren't formal, it really were a Laurent series type expansion, which converges, then this would be a Taylor series part. This would be the polymorphic part. And this would be the singular part of the Laurent series, but written as an exponential. So Y consists of a constant matrix independent of zeta whose entries are just exactly the eigenvectors in one life of the Lax matrix at that point. That's a fixed number. And then you have a series which is not necessarily convergent. This is just a formal, just plug it in, and you can compute the parameters that come out in a unique way. So there's an associated formal series solution. And the holomorphic part on the left is here, and the singular part is the exponential of such a matrix. You see, this has a pole, and it also could have a log zeta factor. The exponential of a log is a power of zeta. This is the Fuchsian contribution. This is the regular singular. These are all the irregular singular. So these, the point is, it's possible. This is just linear algebra. You can find it in standard books on differential equations and their singularity structure. You can choose this formal series so that the singular part only consists of diagonal matrices. All of them are diagonal. And the elements, the diagonal matrix elements, carry 3 indices. So the rank, so we go from 1 to R. The order, the degree of the poles, we go from 0 to the Poincaré index, and the location of the pole. So we have a triply indexed set of parameters, which we will hence call the Birkhoff invariants. These will be, aside from the poles, these will be the deformation parameters of the system. All of them, except this part. That will not be, that's a sort of redundant parameterization. I don't want to go into it, but it's just starting with J equals 1, that it's a Birkhoff parameter. So you can count out how many there are. It's uniquely determined from the structure of the Lax matrix. And the generic situation where all these eigenvalues. So when they cross over, you have phenomena that have to be dealt with. The higher order, but are non-linear. So now what about these folks? The statement is that in a neighborhood of every irregular singular point, there you can divide it up like a pie, like an apple pie, into slices of pie. The number of slices is equal to twice the Poincaré index. So here's what it looks like. Okay. In this case, the Poincaré index is 8. I put the irregular singular point with the Poincaré index 8 in the middle, and I slice it up because I think you have paths that start at infinity and go out to infinity, but don't hit any singularity. That's not important for us now. But the main point is that we have 16 different sectors. These are called the Stokes and anti-Stokes sectors. And in each sector, we can choose the actual solution to be such that it has the form of the formal solution. So understand what I'm saying. We're taking an actual solution in this sector. We take another actual solution in this sector, which is related to it by right multiplication, by the constant matrix. That's the Stokes matrix. But in this sector, the actual solution has exactly the diagonal form that the formal solution has. But this does not. This does. In this sector, this one has the, so they all have the same formal form, but the actual solutions are different because they're in different sectors. That's this is the Stokes in a nutshell. I'm describing Stokes phenomena. So that means that even the asymptotics are not neighborhood asymptotics. Even if it's an asymptotic series, which it doesn't necessarily have to be, the formal series might be just not even asymptotic. Asymptotic means some convergence properties, but you don't need that. But you could have an asymptotic series which is well defined in a punctured neighborhood. These guys are not. They're only defined in sectors. And the fact is that it's part of Birkhoff's theory that they're related by these Stokes matrices. You can actually see that within some standard basis changes, you can always arrange so that the Stokes matrices are either upper triangular or lower triangular, They alternate actually between upper and lower, and you only have zeros and ones entering. So those are called the Stokes parameters. I'm not going into that. The main thing is doing that under the deformations that we're going to encounter. We haven't found the deformations yet. That's the result of the Jim thing. So we're going to look at, oh, sorry, and if you have a whole sequence of Stokes matrices and goes zip around the whole cycle, that almost but not quite reproduces the monodromic matrix. That's exactly where you started, except that there's an extra factor which I will go into, which has to do with the connection. So once you know the S's and the C's, you also know M. So that's not quite independent. Or you can forget C's and only look at M and S, and that's sufficient data. Anyway, so the generalized monodromy data, according to Beercroft, are these things. The monodromy matrices, the Stokes matrices, we're going to be looking, or at least Jimbo Miwa put their finger on what is the most general deformation of the lax matrix that's possible, given by first-order differential equations that preserve them now. I think I'm going to run into time trouble if I'm going, so let me accelerate a little bit. So, for better or for worse, everything on the screen has already been defined. This is a uniquely determined thing, determined actually algebraically in a recursive way from the lax matrix. So is Y. So all of these things are uniquely calculable in terms of the entries of the lax matrix. Define this for each triplet UJA. Define this. The conjugation of the derivative of T of the exponential part by the, say, holomorphic part. That's diagonal, so and also define for each pole this similar object where we're differentiating the spectral location pole. That is going to be our infinitesimal isomonodromic information matrices. That will define our equations, which generalize the DDT equation for Painlevé 2 and the DDCU equation for singular, just Lorentz, the principal part of the Lorentz extension. So here's the system which Jimbo Miwa wrote down in 1981 or something like that. And this is the generalization of Schlesinger's theorem. The statement is that if you look at this overdetermined system, which involves derivatives in the spectral parameter direction and in the direction of all of these parameters, Birkhoff parameters and location of the poles, if this is a compatible system, that means the cross derivatives are equal. Then the monodromy data generalized is invariant, does not depend on the P and the C information. That's an isomonodromic, rational isomonodromic information. And here, this is the written out in detail with zero curvature conditions in all possible directions. So easily have a connection. The dimension is given by how many information parameters there are. And now I'm going to, okay, now I have to, I have 5 minutes. I have to tell you the Hamiltonian structure. Well, I don't think I'm going to get very far, but I have to tell you the leading points. The main point is we generalize the Poisson structure that we had before in the case of higher order singularity by this formula. And this was already known in the classical theorem, in the 1980s approach to integrable systems as isospectral deformations. This is not a new Poisson structure. But what I found in the 1990s was this can also be used to explain isomonodromic systems. So this bracket, just take it as a rule. Think of L of Z and L of W as matrix, as the elements of a matrix value rational function of the variables, and their Poisson bracket can consistently be written this way. In the old days, this was called the Leningrad brackets. There's also a quadratic version of this. I don't want to trouble with it, but basically this is the R matrix structure that's underneath this. So this theorem, the R matrix theory, says that if you take any two conjugation invariant functions of your lax matrix, I'm calling this add star because I am thinking of it as the dual of root algebra. Any two conjugation invariant functions Poisson commute. That's part of the theory. So those are the coefficients of this spectral curve. And second statement is that the Hamiltonian vector field generated by such a spectral invariant is always a commutator. And the commutator can be computed in a very standard way. You take the function, which is a function on the dual of this loop algebra, take its differential, that's in the dual space. It's an element of the loop algebra. So DH is in the loop algebra. And then apply this endomorphism, RS, which is really the R matrix. In this case, it's the so-called split rational R matrix. You just divide up your element into positive and negative frequency. I'm thinking of a unit circle Fourier analysis with positive and negative frequency. And you take those two pieces, the part that looks like positive powers of Z, where Z is a unit circle, and negative powers of Z. Split them, and turns out for an isospectral system, it doesn't have all these parameters. It's a convex linear combination of projection to Y plus or projection to Y minus. And the statement is take this projection, and that is the Hamiltonian vector. Just it's always a commutator. That's part of the thing. Now I'm in difficulties of time. I really have talked too long. All right, I think what I'm going to do is to say this. I have to state a few facts. The phase space is the space of all lax matrices of the rational type that we looked at. It's easy to calculate the dimension. The Birkhoff parameters can be thought of as functions on this phase space. Theorem, not known before. Those Birkhoff parameters, together with the rotation of the pole, are the center of the Poisson. They generate the center. They are all the Casimirs that there are. So that's given an interpretation that was not in Gino, it was not in Birkhoff. The Birkhoff deformation parameters are spectral invariants, which are Casimirs. They don't generate flows because they Poisson commute with everything. But they will be the deformation parameters in the isomonodromic system. And we do have Hamiltonians as well, which are in a sense dual to these. So the main statement is, if I take the eigenvalue of the lax matrix at the singular point, and it has an eigenvalue on each, in this, it's a multi-sheeted Riemann surface, which has as many sheets as R. On each of these sheets, you have an eigenvalue, and you can make a Laurent expansion of that eigenvalue around that point, just like you can with the lax matrix. The polar parts are given by the Birkhoff invariants, the coefficients of the polar parts. The first mirror image holomorphic parts in the Laurent expansion are also spectral invariants, but these are the Hamiltonian that drive the system. They come in pairs. The deformation parameter, the Hamiltonian, so on. So these are explicit ways to write it down. This is just in Hamiltonian terms of phase space, but here it's evaluated on a solution manifold. So what's in blue is exactly Birkhoff's definitions of these things, or Miwa definitions. So I think I have to fast forward and just say the following. As I said, the Casimirs are the T's and the C's, where J starts with 1, not with 0, and you got the logarithmic one. And there's a differential form on the space of parameters, which is defined by taking residues of those guys that we had before. I mean, this is a differential form in two ways. You've got a differential with respect to the parameters and a differential with respect to the Z, the spectral parameter. We take a residue of this, that leaves us with the one form of these parameter space. That, according to Miwa, is a closed form. Its differential is 0, and that it's 0 exactly because all of the Hamiltonians commute. And it's the differential, what we call the logarithm of a tau function. That's where the tau function appears. Its coefficients in terms of all of the information parameters are the Hamiltonians that drive the system. And I have to just leave out everything. There is a very subtle point, which is, I believe that completely from the top, which is what is the analog of the explicit derivatives? Remember, we took an explicit derivative in the A2 case with respect to the t parameter because it was sitting there. We could take an explicit derivative over and above the Hamiltonian derivative. And the same thing for Schlesinger. We had just an explicit derivative of the piece of the Lax matrix that depended on the whole. And we had this curious equality between partial derivative of the Lax matrix with respect to the deformation parameter and partial derivative of the deformation matrix with respect to the spectral parameter. Those are equal. The net result is that there is a sense in which we can always have, these are the explicit derivatives. They are the generalization of what in Painlevé 2 were just explicit differentiation of the Lax matrix with respect to T and explicit differentiation of the Lax matrix with respect to the poles. So I have to justify all this because the way that they're defined is exactly so that this equality is satisfied. I'm using that as a definition, and I don't have time to follow it up. So I have to come with the sort of grand conclusion. All of this is consistent. The various explicit derivatives really do represent vector fields which commute amongst themselves. They're not so explicitly seen as they were in the two examples, but they are functions of the face. And so I think I will finish with a picture which describes what really is going on. And this is what we've proved with Mathématique. The conclusion is that all of the Jimbo-Lewa equations really are Hamiltonian, but non-autonomous Hamiltonian equations. The Hamiltonians we've identified, the deformation parameters we've identified, and the picture is this. This is not quite a global picture, but it's close to a global picture. What I'm describing here is now I'm taking the space of all Lax matrices, rational Lax matrices. Okay, that's a Poisson manifold. It has the Leningrad bracket that I wrote down before. And the symplectic leaves are the level sets of the Casimirs, but we know what those are. They're the Birkhoff invariants. So we set those equal to constants. And it's the pole locations, which we also set equal to constants. So this is a symplectic foliation. In addition to that, we have the explicit derivative vector fields, which are transversal to that. This is, let's write it this way. This is the explicit derivative with respect to P0 with respect to T mu AJ. So this is a transversal distribution. We have two distributions, symplectic foliation, and we have the transversal distribution generated by those vector fields parameterized by the Casimirs. That's a direct sum decomposition. So it's transversal. And the statement is that if you have a point in this phase space, and if you project, so I've written this with a horizontal, but there is a vertical component as well. If you project the deformation vector fields to the total isomonodromic deformation, you get two parts. You get a transversal part and a Hamiltonian part. So you get the part which is the Poisson bracket. Okay, so these are the Hamiltonian flows, but it's a projection. It's when you ignore the transversal Casimir variables, that's a Hamiltonian system. To that you must add. So let's call that the Hamiltonian vector field. To that you must add the explicit derivatives, which are well defined as vector fields. So this is explicit derivative. That acting on the Lax matrix gives you its total deformation. So that's the other side of the equation. That's the DL, L, DL, DT, mu IA, which we wrote down explicitly. So that means that we have a completely Hamiltonian description of all of the isomonodromic rational isomonodromic deformation equations An explicit way to write them, an explicit way to calculate the deformation matrices is also the deformations with respect, I won't write it, but the deformations with respect to the pole locations. These also are spectral invariants. The compatibility of these conditions give you the invariance of the monodromy in the generalized sense, and that's the story. So that much.
Thank you very much for the very nice talk. Are there any questions in the audience or online?
Is this an archive, yeah? The work is
And it's a series of papers. So the most recent one appeared in Jan this year. It's in 2023. It's in.
Well, I would like to take a look because there are already structures to define vectors, things like that. I think it's not about what, and we have a parameter, but you can say the symplectic time parameterized. You have co-symplectic, you have other transformations. I don't know if you have taken a look or you have an idea.
Yes, we understand that question. What he's saying, which is absolutely correct, what you're saying is that simply defining these Casimir functions on the space does not define vector fields along which you can differentiate, because you need to have a complement. Partial derivatives, you have to say what is fixed. So when you're going in the horizontal direction, you're fixing the vertical variables. When you're going in the vertical direction, you're fixing the horizontal variables. And that means that there really is a bundled structure here, a canonical structure in the Poisson sense. But what we have is a global section which allows us to write it as a product space. That's just part of the theory. I can't describe that in this hour. But the subtle part is exactly what you're worrying about, namely, how can we justify calling these transversal derivatives when really they're just functions? But we don't define them as functions, we define them as vector fields. What we have to check is that these vector fields all commute, that they all preserve the Poisson structure, and they preserve the symplectic structure. All of these are theorems which are proven in the paper.
I will take a look. We'll be interested.
Yeah.
Okay, thank you. Any other questions? If not, let's thank John again.